Okay, so today I'm going to talk about Bayesian deep learning. It's a probabilistic framework we have been developing to unify deep learning and graphical models and to bridge the gap between perception and inference. So, as we all know, deep learning has achieved significant success in recent years. To some degree, it already has the ability to see which corresponds to tasks like visual object recognition. It also has the ability to read and hear to some degree. That corresponds to tasks like text understanding and speech recognition. So these are all fundamental perception abilities enabling a system to perceive the environment. However, in order to have a truly functioning AI, we also need the ability to think, which corresponds to tasks like inference and reasoning. And here by inference and reasoning, I mean the ability to handle complex relations, conditional dependencies, and randomness among the variables. So basically, we have two main classes of tasks in AI. The first class is perception tasks like visual object recognition. And these tasks can be easily completed by normal human beings. Like when you read a book, you know naturally that what each sentence means. And naturally, deep learning is very capable and suitable to handle these kind of tasks because it can efficiently handle high dimensional signals like text, images, and videos. And there's another class of tasks, what we call inference and reasoning tasks. And these tasks would involve a higher level of intelligence, like decision-making, data analysis, and logic deduction. And we have this another class of models called graphical models. And these models are particularly suitable to handle these kind of tasks because it can naturally handle these conditional dependencies and complex relations among different variables. So if you look at this one, this graphical model, it particularly tries to reason the probability of wet grass given the probability that sprinkler is on or that it's raining outside. However, graphical models, they typically cannot handle high dimensional signals efficiently. So if we plot it in a figure, we can see that deep learning is good at perception tasks and graphical models are good at inference and reasoning tasks. However, in the real world, these two classes of tasks often entangle with each other. For example, you cannot accurately reason about the relation between two articles unless you can fully understand them. So naturally, what we desire is we want to combine the power of deep learning and graphical model into a single principal framework to get the best of both worlds. And we call this framework we develop Bayesian deep learning. Usually in a Bayesian deep learning model, we have a graph, we have a deep component, which is usually a probabilistic deep learning models. And we also have a graphical component, which is usually a graphical model. And the deep component will handle the content understanding of the task, like understanding the text or processing the images. And the graphical model will handle the conditional dependencies, modeling the causal relations between different variables. And note that this graphical component is probabilistic in nature. So in order for the deep component to be compatible with the graphical component, we also need it to be probabilistic. And since it's a unified Bayesian model, we can naturally adapt the algorithms like MAP, MCMC, or variational inference to learn the parameters. As an example, if you look at medical diagnosis, the deep component is like a doctor examining the patient's medical images or medical records or various signals. These are all very high dimensional stuff. And the graphical component is like the inference and reasoning, the causal inference happening in the doctor's head. On one hand, being able to see these medical images is the basis on which the doctor can perform these diagnosis and reasoning. And on the other hand, accurate diagnosis can also help the doctors to better understand these medical images. There's another example in movie recommender system. The deep component is handling the content understanding of the movie, like understanding videos, the plots, the actors, And the graphical component will model the preferences and similarities between the users and items and perform the actual recommendation. Now, on one hand, better understanding of the movie can definitely boost the recommendation accuracy. But on the other hand, if you analyze the preferences and similarities correctly, you can also help, like in turn, better understanding the movie themselves. So these two components are actually helping each other. And formally, we can represent all these Bayesian deep learning model using graphical model, where we have a deep component and a graphical component connected to each other to enable information exchange. And here, we partition the variables into three sets. We have the deep variables, which are usually the variables inside the deep component. And these variables are drawn from relatively simple distribution to ensure computational efficiency. And we have the graphical variables, which are variables inside the graphical component without direct connection to the deep component. And these variables are often drawn from relatively complex distributions in order to handle these complex relations and conditional dependencies among different variables. And we have the hinge variables, which are variables inside the graphical component with direct connection to the deep component, so that this whole model can be jointly learned or end-to-end. And after the proposal of our framework, it has been used by us and others in various applications, including recommender systems, topic models, control, link predictions, and healthcare.